Okay, so this is a video on indirect proof and inequalities in triangles. Um, there is a lot more in the notes than what is going to be in this video, and what I've come to realize is that I want to cut the video down here to the most salient points, but I'm going to leave the details in the notes for you if you'd like to see them later on. So we're going to start with the idea of indirect proof. And kind of work our way out. When you do an indirect proof, what happens here is you take 4 steps. You first identify your conjecture, so what you're trying to prove. Number 2, you assume its opposite. Number 3, you reason from that opposite to a contradiction. And number 4, you then can now conclude that the opposite is false, which means that your conjecture is true. So this is like a way of leveraging the contrapositive in order to prove something, but you're doing it indirectly. So we're going to use this to talk about a series of inequalities in triangles, and we'll prove a couple of them by using an indirect proof. Okay, so the first theorem that we're going to go after is a pretty straightforward one. It says that if you have a triangle and you look at the largest angle, it is going to be across from the longest side. The smallest angle is going to be across from the small side, and the medium size angle is going to be across from the medium side. So the larger angle is always opposite the larger side. So we're going to assume that, not assume, but the first way that the theorem goes is like if I call this R, Q, and S, right? And ultimately I say that RS is bigger than RQ, then the theorem follows that the measure of angle RQS, the angle across from RS, has to be bigger than the measure of angle RSQ, which is the angle across from RQ. So if I have a big side, the big angle must be across from it, and if I have a small side, the small angle must be across from that. Now, what we're going to do is we're actually going to prove this converse, and we'll kind of work from there. Okay, so we just said that if I have a large side, one side is longer than the other, then the angle opposite the large side must be larger than the angle opposite the small side. So what we're going to do here in this proof is we're going to go the opposite direction. I'm going to say I have a triangle PQR, and I'm going to be given that the measure of angle P is bigger than the measure of angle R. And what I want to prove is that QR is bigger than QP. So what I do is I assume the opposite. So if I'm doing an indirect proof of this, I'm going to assume that QR is not bigger than QP. Well, this implies that either QR is smaller than QP or QR is equal to QP. Okay, so case 1 is that QR is smaller than QP. Well, from our last theorem, the one that we just proved minutes ago, if the QR is shorter than QP, which it doesn't look like in the diagram, right? But that means that the short side has to be across from the short angle. So QR is across from angle P, and that would mean that angle P would have to be smaller than the angle across from QP, which would be angle R. So the measure of angle P would have to be smaller than the measure of angle R. But this is a contradiction, because that contradicts our given, which says exactly the opposite. So this cannot be true. So it's still possible that QR could be equal to QP. But if QR is in fact equal to QP, that means I have an isosceles triangle. So by the isosceles triangle theorem, that means that angle P has to be equal to the measure of angle R, which again contradicts our given. So no matter what kind of negation I try to do here, the negation always causes a contradiction. So my assumption here has to be false. If the assumption is the opposite of what I'm trying to prove, and the assumption is false, that means that what I'm trying to prove has to be true. So what have I proven? I've proven that if P is the big angle, then the side opposite it must be bigger than the side opposite the small angle. So I have now the theorem and its converse, and they're working both ways. Okay, another theorem that we need here is simply what's called the triangle inequality theorem. This theorem says that if I have any triangle, and I'm going to label the lengths of the sides here A, B, and C, then all three of these inequalities, A plus B has to be greater than C, A plus C has to be greater than B, and B plus C has to be greater than A. So if I pick any two sides of the triangle and add them, it has to be greater than the third side. Now, there is a proof of this in the printed notes. It's a little bit long and a little bit tedious, but it is there for you to inspect. But this is a big theorem that you're expected to know. Okay, so hold on to that. It's going to come up more than once in this course. Okay, now we're going to move into a couple of theorems that have to deal with more than one triangle. Okay, and one of these is what's called the Hinge Theorem. And the Hinge Theorem basically says that if I have a triangle that has two congruent sides to another triangle that has two congruent sides. So I'm going to make a triangle there. I'm going to make another triangle there. We call this one ABC. We call this one DEF. And the measure of angle ABC is bigger than the measure of angle DEF, then segment AC, or this length of AC, the length of AC has to be bigger than the length of DF. So this is similar to the theorem we saw before, but it's now involving two triangles. This thing is a really complicated thing to prove. Again, a good proof for it is in your notes. I'm not going to work through the entirety of that proof because it is exceptionally long and you would just get lost listening to me say it. So if you want to dive into it, you can, but knowing what the theorem says is more important. That if one triangle has two congruent sides and the included angle is bigger than two congruent sides and the included angle of the other, then the opposite side has to be longer and the other opposite side has to be shorter if this angle is bigger than that one. Now the question is if this side is longer and that side is shorter, do the angles have to follow suit, and that's going to be the converse to the Hinge theorem. Okay, so the converse to the Hinge theorem basically says the opposite of what we said before. If this is triangle ABC, and this one is triangle DEF, and this is congruent to this, and this is congruent to this, but AC is bigger than DF, then this should imply that the measure of angle ABC is bigger than the measure of angle DEF. Well, this can be fairly straightforward proven. There's a similar proof to this in your notes. You do it by contradiction. So we're going to assume the opposite. We're going to assume that the measure of angle ABC is not bigger than the measure of angle DEF. Again, this gives me two cases. Case 1 being that the measure of angle ABC is smaller than the measure of angle DEF, but by the Hinge theorem, that means that AC has to be smaller than DF, which is a contradiction of the given, right? Which is exactly the opposite of the given, so that's no good. And if I use case 2, that the measure of angle ABC is in fact equal to the measure of angle DEF, then in that case, that means this angle is congruent to that one, which means that triangle ABC is congruent to triangle DEF by SAS, which means that AC must be the same length as DF by CPCTC, and that again is a direct contradiction of the givens. So both cases that are possible from the assumption both create contradictions, which means that the assumption is again false, which means that the conclusion that we want has to be true. So there you go, that's proof again by contradiction. Okay, so let's just get the important takeaways from this. You have a set of 5 inequalities. You have one within within one triangle, which says that if I have a large size, big angle has to be opposed to large side. Small angle has to be opposed to small side, right? So we can go from side to angle and side to angle. Likewise, big angle has to be across from big side. So we can go from angle to side, and small angle has to be across from small side. We can go from angle to side. The same thing works with the medium sized ones, but we concentrate on one being bigger than the other. The second one is the triangle inequality, which says if I have A, B, and C, A plus B always has to be bigger than C, A plus C always has to be bigger than B, and B plus C always has to be bigger than A. Pick any two sides, it has to be bigger than the third one. Hinge theorem works with not one, but two triangles, right? And we're saying that if this side is congruent to that one, and this one is congruent to this one, and this one is a big angle, it has to be across the large side. And this one is a smaller angle, it has to be across from a smaller side, and that goes both ways, right? The big angle has to be across from the big side, small angle from the small side, or the large side has to be across from the big angle, small side has to be across the small angle, and we call that the Hinge theorem. We refer to this as the triangle inequality. And this really is just a theorem. It doesn't have a name in specific. And if you want to look at the notes, all of the proofs for this are in there. Again, some of them are a little bit tedious, so I'll let you, do that on your own. I'm not going to require you to do anything that tedious for your assessments in this class, but it's good to know that they just didn't come out of nowhere. All right, thank you.